Welcome to AI Academy. I'm your host JD. In today's episode, we are diving into two fascinating concepts in probability theory: the concept of independence and the birthday paradox. Whether you are new to probability or looking to solidify your understanding, this episode is for you. Let's start with the concept of independence. In probability theory, two events are said to be independent if the occurrence of one does not affect the probability of the occurrence of the other. This idea is foundational in probability and has wide applications, especially in fields like machine learning. For example, consider tossing a coin twice. The outcome of the first toss does not affect the outcome of the second toss, whether the first toss results in heads or tails. The probability of getting heads or tails on the second toss remains the same. This is an example of independence events. Now let's take a different example. Imagine you are playing a game of chess. Each move you make is influenced by the moves that have been made before it. This means the probability of making a specific move is independent on previous move. Therefore, these events are not independent. Understanding whether events are independent or dependent is crucial when calculating probabilities, as it affects how we approach and simplify our calculations. Let's apply what we've learned about independence to calculate some probabilities. Imagine a school with 100 students. Half of them, 50 students, like playing soccer, and the other half do not. If we randomly split these students into two equal groups of 50, how many soccer fans would you expect to be in each group? Since the students were randomly assigned to the two groups, the split should be roughly proportional, so we'd expect about 25 soccer fans in each group. This estimation relies on the assumption that the students' preference for soccer are independent of which group they were assigned to. Now consider a different scenario. In another school with 100 students, 40 like playing soccer and 60 do not. If these students are randomly split into two groups, one with 30 students and the other with 70, how many soccer fans would you expect in the smaller group? Since the preference for soccer and the group assignment are independent, we can estimate that 40% of the students in the smaller group, or about 12 students, will like soccer. One of the key tools we can use when dealing with independent events is the product rule. The product rule states that the probability of two independent events both occurring is the product of their individual probabilities. Let's consider an example. Suppose you toss a fair coin 5 times. What's the probability that it lands heads up all 5 times? Since each toss is independent, we multiply the probability of heads on each toss. 1/2 times 1/2 times 1/2 times 1/2 times 1/2, which equals 1/32. The product rule can be extended to any number of independent events. For example, if you roll a fair 6-sided die twice, the probability of getting 2 sixes is 1/6 times 1/6, which equals 1/36. If you roll 10 dice, the probability of getting 10 sixes is 1/6 carried 10. A very small number is indeed. Now let's move on to one of the most famous problems in probability, the birthday paradox. The birthday paradox explores that the probability that a group of people, at least 2 individuals, shares the same birthday. At first glance, you might think that the chances of this happening are low, especially in small groups, but the results might surprise you. Imagine you are at a party with 30 people, excluding yourself. What do you think is more likely? That no 2 people shares the same birthday, or that at least 2 people do? Surprisingly, it's more likely that at least 2 people share a birthday. The probability of no shared birthdays is only around 30%. Let's break it down mathematically. For simplicity, let's assume that there are 365 days in a year, and no one were born on February the 29th. For the first person, there are 365 possible days for their birthday. For the second person, the probability that their birthday is different from the first person's is 365. For the third person, the probability that their birthday is different from both of the previous birthdays is 365. The pattern continues as we add more people to the group. The probability that all 30 people have different birthdays is the product of these fractions, which comes out to about 0.294 or 29.4%. Therefore, there's a 70.6% chance that at least 2 people share a birthday. As the group size increased, the probability of shared birthday increased rapidly. For example, with 23 people, the probability of at least 2 sharing a birthday is over 50%. With 50 people, the probability jumps to 97%. This result is why the birthday paradox is so fascinating and highlights the surprising nature of probability. In this episode, we've explored the concept of independence and its role in probability theory, along with the interesting birthday paradox. Understanding these concepts is crucial, not just in theoretical contexts, but also in practical applications like machine learning. I hope you found today's discussion enlightening. If you have any questions or topics you'd like us to cover in future episodes, feel free to reach out. Until next time, keep exploring the fascinating world of AI and probability.